In this lecture, we will start a new topic of symmetrical components. This topic is the building block for the analysis of unsymmetrical faults in a power system. So, before going on to the topic of unsymmetrical fault analysis, we should try to understand it firmly that this concept will be very useful for us in doing various calculations in unsymmetrical faults on a power system. Now, in 1918, C.L. Fortescue devised a method of symmetrical components according to the theorem presented by that fellow in his paper published in AAEE, that is which is now IEEE. According to that theorem, it was told that for n phasors which are related with each other, and let us say those phasors are unbalanced, then what we can do, we can make n sets of n phasor each which are balanced with each other. That is, for example, let us say there are n number of phasors which are unbalanced. These phasors are related with each other, okay, but these are unbalanced. Now, according to that theorem, what we can do, we can make n number of sets. Let us say set number 1, 2, 3, 4 up to n, and each set of phasors will be having n number of phasors, that is 1, 2, 3, 4 up to n phasor in each set. Okay, and each set will be balanced. Now, if you want to know the definition of the word balanced, you should try to watch one of the earliest lectures of this course in the beginning. However, just to briefly review, balanced means that these phasors will be having equal magnitude and similar phase angles. Okay, so all the phasors in each set will be balanced with each other. That is, they might be having some different relationship with each other in the two different sets, but within a set, these n phasors will be balanced. Okay, so this is the theorem that was given in 1918. This was published in a paper in AAEE, which is now actually IEEE. Okay, and the person who gave the theorem was C.L. Fortescue. Okay, now typically this power system is a three-phase system, but in every textbook we are shown symmetrical components of a three-phase system. But to grasp this concept more firmly, what we will do, we will try to understand what will happen if there are four phases. How we will define the symmetrical components of four-phase system. Now, once we understand that thing, then the symmetrical components of a three-phase system will be very easy for us to understand. Now, let us see how to determine the various symmetrical components of a four-phase system that we will see in the next slide. Now, let us say that I am having a four-phase system, okay, and I am having four phasors comprising four-phase system, but these phasors, let us say, are unbalanced. You see, these phasors are 4 in number and they are unbalanced. That is, the length of each phasor is different and the angle between them is also different. Okay, so these phasors, let us say this is phasor A, this is phasor B, I represents the, let us say these are current phasors. This is IC and ID. These phasors represent a four-phase system which are unbalanced. Now, according to the theorem, what we can do, we can bifurcate or break these phasors in 4 set of phasors, that is first set, second set, third set and the fourth set, and each set will be having 4 number of phasors. That is, there will be 4 phasors in first set, similarly 4 phasors in second set and 4 phasors in third set and 4 phasors in the fourth set. Now, by adding the component from each set, I can get all the phasors. Now, how to determine these components in each set? There is a thumb rule except for the two-phase system, because two-phase system is typically not satisfying the definition of all different definition of the angles for various kinds of phase systems. So, other than the two-phase system, there is a thumb rule that the angle between the phasors of set number k represents the set number of n phasors, is given by k into 360 degree divided by n. Okay, so for our system n is equal to 4. Okay, so this term is nothing but 360 over 4 is equal to k into 90. So for the set number 1, k will be 90. It implies that the angular difference between the components of each phasor in set number 1 will be having 90 degree phase difference. So let us say I want to draw the 4 phasors of the first set. What I will do, I will draw the first phasor. Let us say this defines the I1A, that is the symmetrical component of phasor A in the first set. Then I1B will represent the symmetrical component of the first set for phasor B. What it will be? It will be simply a phasor of the length equal to this phasor only and at an angle of 90 degree. So this is I1B. Okay. Similarly, what will be I1C? I1C will be the symmetrical component of the first set for the phasor C, and it will be having an angle of 90 degree with respect to this phasor I1B. So this is I1C. Similarly, there will be a symmetrical component for the fourth phasor in the first set. This is I1D. Again 90 degree angle, and since it is now 360 degree complete, it will be also 90 degree angle. Now the conditions are that the magnitude of each phasor is equal and the angular difference between the corresponding phasors is 90 degree, which has come out from here. Okay, now let us draw the components of the set number 2. Now for the set number 2, k will be 2. So the angular difference between the component of set 2 will be 180 degree. Okay, so what I will do, I will try to draw the 4 components of set number 2. Let us say this phasor represents the symmetrical component of phasor A for the second set. Okay, so the symmetrical component for phasor B, for the second set will be having a phase difference of 180 degree. So I2B will be this phasor. Okay, now I2C will be having a phase difference of 180 degree with respect to I2B. So again I2C will be the same phasor as I2A. So it is I2C also. Now I2D will be having a phase difference of 180 degree with respect to I2C. So I2D will be in this direction. So these are the 4 phasors for the second set. This is the second set. This is the first set. Now let us come to the third set. Now for the set number 3, K will be 3. So the angular difference will be 270 degree between the phasors. Now let us draw the phasors of the third set. Let us say this is the phasor for the phase A in the third set. Okay. Now what I will do, I will try to draw the phasor for the phase B in the third set. Now that phasor will be having a phase difference of 270 degree with respect to this phasor. So this angle will be 270 degree. This will represent I3B. Now here I have already told that these phasors will have equal length, I2B, I2C, I2D. Similarly, these phasors are having equal length. I3A is equal in length with I3B. Now let us draw I3C. Now I3C will be having a phase difference of 270 degree with respect to this phasor. So where it will come? It will come here. So this phasor will represent I3C. Okay. Now where will be the I3D? That is the sequence for the phase D for the third set. Here it will be I3D. Now as I already told that these phasors have equal length. Okay. Now let us draw the phasors for the fourth set. Now for the set number 4, this value of K is 4. So it represents 360 degree. Okay. So you see all those phasors will be having this direction only. Let us say it is I4A, then I4B will be having 360 degree phase difference. That is same direction. It will be I4B, I4C, I4D. That is all the phasors will be having this thing, and the lengths are equal for these phasors. Okay. Now we will write these pictorial representation in terms of the equations or the algebraic equation using the operator J. Now we know that multiplication with operator J simply means that we are multiplying or increasing the phase by 90 degree. Okay. Now let us see how to write this thing in the equation form. Now, as I already told that IA is broken into 4 sets. The first set, the second set, the third set, and the fourth set. That is, to get this IA, we will have to add this phasor, this phasor, this phasor, and this phasor. So by adding these phasors, I will get IA. Now IB will again be I1B plus the second set component, the third set component, and the fourth set component. For phase B. Now I know that I1B is nothing but 90 degree ahead of I1A. So J into I1A. Similarly, I2B is nothing but, where is I2B? It is 180 degree ahead of I2A. That is J squared I2A. Similarly, for I3B, for I3B, it is 270 degree ahead. That is J cube times ahead. I3A. And I4B is simply J4 times or 0 degree ahead of I4A. Now I will use these values in this equation. Okay. So IB comes out to be J I1A, J squared I2A, J cube I3A, and J4 I4A. Okay, let us say this is equation 1, this is equation 2. Similarly, for IC, it can be broken into 4 parts, 4 components: I1C, I2C, I3C, the fourth set for the phase C. Now I1C is nothing but J square times I1A. So it is J square times I1A. Now I2C, this is I2C, it is again J4 times I2A. Now I3C, this is I3C, it is J square times, or I can write it as J6 times. J6 times I3A. J6 times means this one and then here. So it is J6 times, and it is only J8 times I4A. Okay, so let us say this is equation number 3. Now writing the ID, it will be ID, I1D is J cube times I1A. It is now coming to the I2D part. Now I2D is equal to J square times of the I2A, or what I can write, J square can be also written as J4 J6 J6 times I2A. Now I3D. This is I3D. What it can be written as? It can be written as J 9 times I3A. What is J 9 times? 3 times here, 3 times here, and 3 times here. It is going out to be here only J 9 times, and it is J 12 times I4A. Let us say this is equation number 4. Now from equation number 4, 1, 2, 3 and 4, I can write down the matrix form that I will write in the next slide. Now let us write equation number 1, 2, 3 and 4 in the matrix form. IA, IB, IC, ID can be written as 1, 1, 1, 1, I1A, I2A, I3A, I4A. You can see that IA is nothing but I1A plus I2A plus I3A plus I4A. Now writing the IB, it is simply J times I1A, J square times I2A, J cube times I3A and J4 times I4A. Similarly, IC is nothing but J square times I1A, J4 times I2A, J6 times I3A and J8 times I4A. Now ID is nothing but J cube times I1A, J6 times I2A, J9 times I3A and J12 times I4A. Now I can see that J square is minus 1, J cube is minus J, J4 is equal to J8 is equal to J12 is equal to 1. Okay. And J6 is equal to minus 1 and J9 is equal to J. Okay. So I will use these values to simplify this matrix. So it comes out to be 1, 1, 1, 1, J minus 1 minus J 1, minus 1, 1, minus 1, 1, and this is minus J minus 1 J 1 into I1A, I2A, I3A, I4A. So in this way I have bifurcated the set of 4 unbalanced phasors into 4 sets of 4 balanced phasors in each set, and I have got the transformation matrix. Let us say this is matrix A. This matrix is the transformation matrix for a 4-phase system. Now by taking its inverse, let me erase this and we will see by taking the inverse how can we get the values of the components in terms of the given phase currents. That we will see in the next slide. Now I have taken the inverse of this matrix A and it comes out to be 1 by 4 multiplied by this matrix. So you can see that I1A can simply be written as 1 by 4 times of IA plus JIB minus IC minus JID. Okay, so I can get the value of this phasor using this equation. Similarly, I can get the value of I2a, this phasor, I3a, this phasor, and I4a, this phasor. Okay, so you see that using, let us say this is equation A and this is matrix equation B. Using these two matrix equations, I can find the symmetrical components or the phasors using these two equations. Now let us try to pictorially try to find, let us say, phasor A from these phasors. Now you see that phasor A is nothing but I1a plus I2a plus I3a plus I4a, and I1a, I2a, I3a, I4a have been determined using these equations. Okay, so I will try to redraw or try to regain the phase A phasor using this equation. So I1a is nothing but like this, I2a is again like this, and I3a is again like this, and I4a is again in this direction only. So sum of all these phasors will give me IA. Now, although I have drawn these phasors I2a, I3a and I4a in the horizontal direction, but the direction of these phasors, if I have taken this phasor as horizontal, direction of these phasors I2a, I3a and I4a could have been different, which should be calculated using this kind of equation, that is equation number B. Okay. Similarly, to find, let us say, phasor B, I want to find phasor B. What I will do, I will add component I1b, I2b, I3b and I4b. That is, I1b is in this direction, I2b is in this direction, so their sum will give me somewhere here, and in this sum I will add I3b, which is here, so their sum will give me something here. Okay, and in this sum I will add I4b. So the sum of these two phasors will give me the phasor IB. If these phasors were drawn using these equations, that is equation number B, then the formation of the actual phasor would give me the right phasor pictorially also. So in this way, what we have seen here, that no matter what is the number of phases in a given system, we can find the symmetrical components for any given number of phasors just by using the thumb rule, where what we have to do, we have to draw the n number of sets, and each set having n balanced phasors, and the angle between them is governed by the equation k into 360 over n, where n is the number of phases and k is the number of set. Okay, but as I already told in the beginning of this lecture, that this thumb rule is not applicable for a two-phase system. For a two-phase system, as we have already seen in the beginning of this course, that a two-phase system comprises of two phasors having 90-degree phase difference. Okay, so this two-phase system will be having two sets, set 1 and set 2, and each set will be having two phasors each, that is first phasor I1a and I1b. Now the phase sequence in the first set will be the same as that in the given phasors. Okay, however, the second set will be having the phase sequence opposite to that of set. if it is I2A, then I2B will be in the opposite sequence. So in this way we can define the symmetrical components of a two-phase system also. Okay, now in the next lecture we will try to determine the symmetrical components of a three-phase system, which is actually in our syllabus, but we have tried to see the four-phase system or a two-phase system to grasp our concept, so that we can firmly know that this is just a mathematical concept which is having a physical consequence also, in terms of understanding the real picture what is going on into the system, and as well as making our calculations easier for unbalanced systems. So if you find that this lecture is helpful to you, then please share and subscribe my YouTube channel. Thank you.